Let's start by diving into the concept of message queue. A message queue, MQ, is a fundamental component in asynchronous communication between services. Think of it as a digital mailbox, where messages wait until they're picked up and processed by a consumer. In a software architecture, an MQ acts as an intermediary that decouples the producer, which sends messages, from the consumer, which processes messages. This decoupling is especially useful in microservices architectures, where different services need to communicate efficiently without being directly dependent on each other. Message queues are commonly used to manage tasks that need to be processed sequentially, balance loads across different services, and ensure that messages aren't lost even if a service is temporarily down. They are particularly effective in scenarios where a system needs to handle a large number of tasks or requests concurrently. From a more technical perspective, a message queue works by allowing a producer to send messages into the queue, where they are stored until a consumer is available to process them. The messages are processed in a first-in, first-out, FIFO manner, although some systems allow for priority-based processing. Popular implementations include RabbitMQ, Amazon SQS, and Kafka, each offering different features like message persistence, routing, and fault tolerance. Message queues are highly reliable, ensuring that messages are stored safely until they can be processed, even if a consumer fails or is temporarily unavailable. They allow for horizontal scalability by simply adding more consumers as the load increases. Moreover, they help in decoupling systems, which can make applications more modular, maintainable, and resilient to changes. Message queues are an excellent choice when you need to handle large volumes of tasks that can be processed asynchronously. For example, they are ideal for background processing tasks like sending emails, processing data, or handling other tasks that do not require immediate user feedback. However, message queues can introduce additional complexity, particularly in managing the order of messages and handling errors or dead letter queues. They can also introduce latency, especially in time-sensitive applications, because of the time taken to enqueue and dequeue messages. Additionally, MQs can be resource-intensive, consuming significant memory to store messages, which can be a limitation in environments with constrained resources. If your application requires real-time processing or has stringent latency requirements, a message queue might not be the best choice due to the potential delays in message processing. In such cases, other messaging patterns like PubSub or direct communication might be more appropriate. Speaking of PubSub, let's explore how that works. Publisher-subscriber, or PubSub, is a messaging pattern where messages, also known as events, are sent by a publisher to multiple subscribers simultaneously. Unlike message queues, where messages have a specific destination, PubSub allows for a one-to-many communication model, where all subscribers to a particular topic or channel receive the message. This model is widely used in event-driven architectures and real-time data streaming applications. PubSub is particularly effective in scenarios where you need to broadcast messages to multiple consumers or services. It's commonly used in real-time applications like live feeds, notifications, or any system where multiple consumers need to react to the same event. In a PubSub system, publishers send messages to a topic or channel, and all subscribers to that topic receive the message. There is no direct connection between the publisher and the subscribers, which means the system is highly decoupled. Popular implementations of PubSub include Google Cloud PubSub, Amazon SNS, and Redis PubSub. These systems are designed to handle high throughput and low latency message delivery, making them ideal for real-time data processing. The PubSub pattern excels in scenarios where scalability and real-time communication are critical. Because multiple subscribers can process messages in parallel, PubSub systems can handle high traffic loads effectively. The decoupling of publishers and subscribers also allows for greater flexibility in system design, making it easier to add or remove services without affecting the overall system. PubSub is a great choice when you need to distribute messages to multiple consumers or when building systems that require real-time updates. For example, it's commonly used in event-driven architectures where various services need to react to changes or events happening in real time. However, PubSub systems can also introduce complexity, particularly in managing message duplication and ensuring that all subscribers receive messages in a timely manner. There's also the potential for increased network traffic, as the same message is sent to multiple subscribers. Additionally, because PubSub systems do not inherently store messages, there's a risk of message loss if a subscriber is offline or unavailable when a message is published. PubSub might not be the best choice if your application requires guaranteed message delivery to each consumer, or if you need to ensure that messages are processed in a specific order. In such cases, a message queue might be a more reliable option. By the way, if you're enjoying this video and want the best practice website for system design interviews, check out our website at systemdesignschool.io. Now back to the video. Deciding when to use a message queue versus a PubSub system depends largely on your application's requirements. If you need to ensure that each message is processed exactly once and by a single consumer, a message queue is the better choice. It's ideal for tasks like job processing, where each task needs to be completed by only one worker. On the other hand, if your application requires broadcasting messages to multiple consumers, such as in a real-time notification system or event-driven architecture, PubSub is more suitable. PubSub excels in scenarios where multiple systems need to respond to the same event simultaneously, providing a scalable and decoupled solution. Consider a real-world example of using a message queue: an e-commerce platform that processes customer orders. When a customer places an order, the system needs to perform several tasks: checking inventory, processing payment, updating the order status, and sending a confirmation email. By using a message queue, these tasks can be handled asynchronously. Each task is placed into the queue and processed by a different consumer, allowing the system to scale as needed. This setup ensures that even during high traffic periods, like Black Friday sales, the system can handle the load without crashing or losing orders. When an order is placed, the order details are sent to a message queue. Different consumers then pick up tasks from the queue. One consumer might handle inventory checks, another processes payments, and a third sends confirmation emails. This approach not only improves scalability, but also ensures that tasks are processed reliably, as messages are stored in the queue until successfully processed by a consumer. Now, let's look at a real-world example where PubSub shines. A live sports application that provides real-time updates to millions of users. As events happen during a game, like a goal being scored, these events need to be broadcasted instantly to all users who are following the game. A PubSub system allows the application to publish these events to a specific topic, and all users subscribed to that topic receive the update in real time. In this scenario, when a goal is scored, the event is published to a sports updates topic. All users subscribed to this topic receive the update immediately. The PubSub system handles the distribution of the event to all subscribers, ensuring that each user gets the update almost simultaneously. This approach not only provides real-time updates, but also scales efficiently to handle the large number of users following the game.